Thank you. I am James Walker from Michigan Tech, here to talk about efficient typing on a visually occluded keyboard. So the motivation for this work is with the advent of consumer affordable head-mounted displays, most of the attention has gone into the entertainment applications of this technology, especially video games. But we were interested in exploring some of the possible productivity applications for HMDs, such as composing documents and writing emails and so forth. However, an obvious problem with this, if you would like to use your physical peripherals, like your physical keyboard, which are both very familiar to everybody and also give extremely good performance, is that you can't see the real world while wearing a head-mounted display, which is clearly a problem. Other work that has investigated this has taken two main approaches, both of which utilize mixed reality. One of these approaches displays a graphical keyboard within the virtual environment in the head-mounted display and tracks the positions of the user's hand so that you can see where they are typing on this keyboard that doesn't actually exist in the real world. And the other approach has been to use external cameras to take video of the real world and superimpose that video within the virtual environment so that, for example, the user can see their physical keyboard and their hands in addition to the virtual environment itself. There are some issues with these other solutions, such as the fact that typing in midair generally results in pretty poor speed and is also, if you've done it, you know that it's actually surprisingly very taxing to type in midair for very long. For the other solution, incorporating video feedback into the virtual environment, this requires the use of extra hardware besides just the head-mounted display, introduces extra complexities into the system, and is prone to certain errors such as the user occluding their own view, like by having their hands over the keyboard so they can't entirely see the keyboard as well as they would like. So the question is, can we enable people to use their physical keyboards while keeping the solution simple and inexpensive? The system that we designed to tackle this problem consists of two primary features, which you can see here on the video. One of them is a sophisticated keyboard input decoder, essentially a spell checker on steroids for correcting users' input. And the other is a virtual keyboard that provides live feedback to the user in the form of flashing the key that the user just hit on the keyboard so that they can see what keys they're hitting. For the decoder, we used VelociTap. We adapted this, which is a decoder created by Professor Vertanen. The way that VelociTap works, it was originally meant as a touchscreen decoder for cell phones and the like, and it uses 2D Gaussians, essentially a probability heat map on the keyboard to determine what key you meant to hit based on the one that you actually did hit. We modified VelociTap for use with physical keyboards by measuring a real keyboard and using the central position of each key whenever you hit that particular key as the input into the decoder. And VelociTap is also trained on billions of words of data. We first conducted a quick pilot study in which we had 5 participants in 3 within subject conditions. One where everything was fully visible, one where only the keyboard was occluded by a cover, and one where the user was actually wearing an Oculus DK2 head-mounted display while they were typing. So what we got from this initial data gathering was, unsurprisingly, participants did the best in the baseline condition. We also saw that the decoder was significantly reducing the error rate in all conditions to levels that are acceptable for many casual productivity and text entry tasks. One thing that was interesting was that users typed much more slowly with the head-mounted display as opposed to just when the keyboard was covered. And we also noticed that when we had the decoder spend more time in post-processing decoding the input, we got a higher amount of accuracy gain, which in our experience is not typical. And we speculated that the reason for this is that there were certain kinds of errors that were not being modeled in VelociTap. For the second phase, we added the virtual keyboard, because the first phase had only used the decoder, and then went on to perform a larger user study. We also added a transposition operation to VelociTap, which is where you hit 2 keys in the wrong order in order to model that common typing error. And then went on to perform a study with 24 participants. We had 2 hypotheses. One was that the virtual keyboard would improve users' typing performance, because we already knew that the decoder would, and also to verify once again that users' typing performance would be worse in the HMD. We had 4 within subject conditions. In 2 of the conditions, the user wore an HMD. In one of those, they had the virtual keyboard on, and in another, they did not. In the other 2 conditions, they did not wear an HMD, but the keyboard was merely covered, the physical keyboard that is. And again, in one of those, the user had the assistance of the virtual keyboard, and in the other, they did not. The results of this study were that with statistical significance, users were faster with the virtual keyboard present than they were without it. And we once again verified that users were typing more slowly with the head-mounted display. The speed here was pretty good, over 40 words per minute in all conditions. The level of accuracy was acceptable for many productivity tasks. And the overall result of this was that participants were able to use their physical keyboard pretty effectively, despite the fact that they couldn't see it, and in the case of wearing the HMD, they couldn't see anything in the real world whatsoever. It's noteworthy that the virtual keyboard improved accuracy, even though it only provided feedback of keys that the user had already hit, because the backspace key was disabled and we did not allow users to go back and edit their input. We conjecture that possible reasons for this could be that obviously the virtual keyboard was providing a visual reminder of the layout of QWERTY keyboards, so that if the users forgot where a key was, they could just look at the virtual keyboard and see it. And in addition, if they had their hand positions wrong, for example, they had their hand positions off the home row, then once the keys started flashing and they saw that the keys flashing weren't the ones they meant to hit, they would quickly realize what was going wrong and could adjust their hand position. So in conclusion, the decoder and the virtual keyboard significantly improved the accuracy of users' input. We were able to get pretty good input speed of about 40 to 45 words per minute, even with a couple of particularly slow users dragging the average down. Accuracy level was around 95%, and our solution does not require any extra hardware, and it's very simple and easy to implement. Thank you.
Thank you, James. Any questions? We have a minute or so for questions. None? Okay. Well, thank you for your talk, and that brings us to the end of the day of talks. Thank you, everyone.